Welcome to a lesson with Dr. Powell. Let's take a look at how we can think about counting the number of configurations of a beaded bracelet with 5 different beads. We've arranged them in a pentagon arrangement, and we've numbered the beads differently to represent the beads all being unique and different. They could be different in color, but here they're different in number. Okay, so for starters, let's think about the different permutations which we could apply to the beads here in this bracelet as we see it, so that it would be the exact same configuration. What does it mean to be the same configuration? Well, pretty much if I were to rotate this, rotate this like 1 bead away, so this one would go this way, that way, just kind of following these arrows. That would be the exact same bracelet. I've just rotated it. I could rotate it once or twice or 3 times, 4 times. I could also flip it and turn it around and look at it the other side. There are permutations that preserve this configuration. In fact, I've listed them out right out here in cycle notation. This one being, for instance, rotating it around once. This one being flipping it across this axis of symmetry right here. Okay, so this collection of permutations that do that is a subgroup called the dihedral group of order 10. It's a subgroup of the permutations on 5 things, which is S5. Okay, so now let's think about a permutation that takes us from this configuration to another one. For instance, this bracelet over here is a different configuration than this one. You can see that because 1 and 2, these colors or these numbers are right next to each other over here. Here they're not. So definitely 2 different bracelets. Okay, now if we think about this, so 1 going to 1, maybe 2 going to 4, 4 going to 2, so that doubles back on itself, swap places. This permutation right here, G, is the one that takes us from here, a configuration over here, to this configuration right here. Okay, now it might be interesting to think about what are the permutations that fix this one. Well, what we could do is you could take a permutation back from something over here and pop it over here, and then you could run an element of D10, which preserves this configuration, and then go back over here again, and everything that actually preserves this configuration could be thought of in such a way. You could call this it's represented right here. So G inverse, so going back, doing a rotation, a 3-dimensional rotational symmetry over here, like flipping it around around this axis, or rotating around so doing anything like that would that's an element of D10, and then after you do that, go back over here via G. So G inverse, do something in D10, then come back. We call that a conjugate subgroup of D10, and in cycle notation, we can see the cycles of the permutations that actually would preserve this configuration over here. Okay, great. Now let's consider, how do we describe the permutations that take us from this this particular orientation in this configuration all over to anything in this configuration? Okay, so you can think of it this way. in the new perspective meaning the new orientation, this is like, yeah, the rotational symmetry group of that, um, of our new configuration that we had over here. So this was our new configuration. This is our original one. And so, right, this is the rotational symmetry group right over here. And what are we applying it to? We're applying it, so if we apply this, so this is how that one can vary, but first let's send our original bracelet over to the place where this can cause that configuration to the variance within that configuration. So notice we run, this is the stabilizer of that configuration. In fact, it is called a stabilizer subgroup. But first we have to go to the original into that configuration running G. Well, notice when you do this, so this is all permutations that actually take us from the original bracelet that we saw and take it to anything in our new configuration. These are all those permutations. Notice that these guys right here cancel. So what are we left with? A coset, a left coset of D10. That means a shift of D10 on this side, like this permutation of anything in that particular subgroup. So we have this coset, the coset G, left coset G, so G composed with the subgroup D10. That gives us all permutations that take us to that one. That's interesting. Because if we can have some distinct cosets, remember, cosets chunk up something. They partition it in a disjoint way, and so it fills it all up. So S5 is being partitioned into chunks. One chunk is D10, and then you're going to have these different left cosets. GD10 would be one of them. Maybe we could label these G1, G2, and if we can find the distinct left cosets, will send us to distinct configurations, and the collection of configurations is in one-to-one correspondence with these cosets. So all we have to do to count the number of configurations is to count the number of cosets that we have of D10. Now all the cosets are the exact same size, and this partitions it completely. D10, and each of these cosets has 10 elements in it, because there's shifts of D10 here, which has 10 elements. So let's think, and we're partitioning up S5. S5 has 5 factorial elements in it. So 5 times 4 times 3 times 2 times 1. It's a 5 right here. So 20 times 6, so that's 120. So we're going to take 120 permutations, and and all these cosets have 10 in them. So that tells us 120 divided by 10. That tells me how many cosets I actually have. We have 12. That means there are 12 different bracelets, 12 different configurations. Now, for terminology, D10 is the subgroup that maintains the original bracelet. It's called the stabilizer subgroup of that. Another thing is that we actually have every permutation of S5 takes one of the configurations to another configuration. Sometimes permutations keep us at the same configuration. Then they would be in the stabilizer subgroup of that configuration, or they might take us to other ones. But this actually produces a group map, or a group homomorphism, that preserves group structure, a function between S5 and the permutations on the actual configurations we're talking about. Maybe we'll let C be this collection of 12 configurations we're talking about. And so we actually have a group homomorphism that goes from S5 to the permutations on that collection of 12 things. So if you want, so we have a group homomorphism that goes to S5 to SC. Well, you could think of SC as being S12 um, here. And so, of course, it just maps into it. And there are, and of course, anything in D10 actually is like the identity. Let's see. Well, anything in D10 will stabilize um, our original configuration. But nonetheless, this right here is a group. Um, this is a group homomorphism. Anytime we have that, we say that S5 acts on C. That's just terminology there. Okay, and not only that, but it acts transitively. That simply means that any configuration can be taken to any other one um, via via a permutation in here. That idea alone, that transitive action, meaning that there's always a permutation that go from one configuration to another, and the fact that this is a group action, um, that S5 acts on C this way. This is a group because there's a group homomorphism from S5 to the permutations on C. Allows us to have a stabilizer subgroup, such as D10 that we can look at the cosets of, and all of its cosets are in one-to-one correspondence with the elements of C. So that's what we're using here in order to make this count. Thanks for watching.